So, okay. So somebody has not understood step method. I will solve one more problem in the step input. So I can consider whatever the entire people who is attending have understood the entire, let's say, non-ideal reactors. See this step method. One more example. Yes, I will do it. One more example. Step. What is difference between step method and pulse method? So somebody yesterday also asked, if we have a pulse experiments, then why do we need to do step experiments? So that is actually another way of conducting a RTD experiments. It doesn't mean that, let's say, we will use step experiments in reality. Reality is, if you yourself will see, step experiment is slightly complicated than, let's say, pulse experiments. Pulse experiment is simple. If stream of white fluid is going, white fluid is coming out, you have injected red fluid. But in the step experiments, you have stopped the white fluid and you are starting the red fluid. So what is continuous fluid? What is non-continuous fluid? You need to identify. Continuous fluid, if you track, you will not get anything because there is a continuous flow of molecules. Clear? So you have to target non-continuous fluid. So you have to target non-continuous fluid. So what is non-continuous fluid in step experiments? White fluid? No. When I stop the white fluid, the reactor is filled with the white fluid. So how that white fluid is coming out of the reactor is RTD. See, if you are attending for the first time, maybe if you are in the third year, you will develop a overall picture of, let's say, what is CRE. So let's say CRE is for reactor design. So then what is it required for reactor design? Let's say for reactor design is kinetics is important. So kinetics means, what is it kinetics? Kinetics means finding out the rate expression. So once you have a kinetics, I will able to select a reactor, or I will able to design a reactor. So you cannot design a reactor without kinetics. That is the first step. So once you have a kinetics, you can select CSTR, you can select PFR, or you can modify a PFR according to your requirement. Let's say I have a reaction A plus B gives C. A is positive order, B is negative order. Then what you do, you will send the A as a bulk fluid and C as a B as a step in, or let's say multi-point injection. Clear? So that is how the concept. So that kind of overall picture. Then what I did in, let's say, chapter 2, I developed a concept of CSTR PFR. What I did in chapter 3, I have developed, let's say, I have extended the envelope to, let's say, multiple reactions. Let's say A gives B gives C, and A gives B, and A gives C. So this is what I have done, let's say, in chapter 1. But imagine that you cannot get a CSTR, you cannot get a PFR behavior in reality. So what is an ideal gas? What is thermodynamics? Thermodynamics is all about define an ideal gas and define an ideal liquid and define non-ideal liquid, non-ideal gas, and you will define, let's say, how a non-ideal gas is, what is the deviation between non-ideal gas and ideal gas. That is how you define, let's say, fugacity coefficients and activity coefficients, and all the story is a simple vapor liquid equilibrium. Clear? So similarly, what is CRE is, in the CRE1 is you are defining the ideal reactors. What is CRE2 is how a real reactor is different from an ideal reactor. Let's say how it is deviating from an ideal reactor. What is the extent of deviation? How do I correct my model to understand this extent of deviation? So clear? So somebody asked me to repeat step and pulse input, so that I have done. Step example, one more example that I will solve it right now. So in pulse experiments, red fluid is not continuous. No, you are adding, let's say, so imagine that you have a house. White dress people are coming in, white dress people are going out. So this is a simple. Let's say every time white dress people are coming into the house, white dress people are going out continuously. Suddenly to the white dress people, you added, let's say, 10 red dress people. Either 10 red dress people continuous? No, non-continuous. The 10 red dress people along with the white dress people you injected. So now you will sit at the exit and then you will count how many red dress people are coming with respect to experiment. Clear? So can I consider that all the students, let's say all the 80 or 85 students who are joining the class have understood CRE overall? I would not say, let's say 100%, maybe more than 80-90 percentage. If you get more than 80 percentage or 90 percentage from the class, then you have captured most of the things. So at a time, 100% guess translation is not possible. No, anybody, even if I am attending for the first time CRE, I could have got, let's say 50-60% only. Later on, by reading, by revision, so you will always get more knowledge. Clear? So multiple revisions is the key to the knowledge. That is what I say to the entire, let's say every GATE student. What is important is how many times you revise is the important thing. Let's imagine that you attended the GATE exam and you are sitting in front of the GATE exam. There is a GATE question in CRE, or let's say heat transfer. Let's say composite cylinders is a GATE question. I don't know what is the equation for composite cylinders. So then you know the concept of heat transfer, you know you are very good in heat transfer, or you are conceptually extremely good. But if you don't know how to write that equation, or if you do not remember that equation, can you solve the question? You cannot solve the question. But how do you remember that equation, or how do you get perfection in every subject is revisions. Revisions is the key to the entire GATE exam. That is what I tell. By end of November, you should stop the entire preparation, start revising the subject. So many revisions. Revision by revision, you will understand that you yourself will feel that your knowledge is enhancing for each revision. So that is what is for me also. Like I'm teaching this CRE at least 100-200 times, but every time when I teach, my knowledge of CRE will improve by, let's say, 0.1% or 0.2%. Clear? So that every revision is important. So somebody is asking this question. I think I am getting this question most of the times. I understood the concepts, but I have a problem in, let's say, solving of the problems. That is a common problem in GATE students. Let's say 90-80% of the students will stuck at solving the problems. That is what I told. So to overcome this one, multiple revisions is one key. Second is solve as many problems as you can. But solve doesn't mean that solve, let's say, test papers of some X institute, some Y institute, some Z institute. First thing is solve all the previous questions. Second thing is solve textbook examples. Third thing is solve textbook backend questions. Suppose, see, it is a simple common sense, like the IIT professors who is setting up a, let's say, GATE exam. Let's take a CRE case. So IIT Bombay is setting up the paper. So the department of CRE in, let's say, IIT Bombay has at least two professors who are experts in CRE. So at least one person is Sanjay Mahajani, who is the, let's say, one of the person who teaches CRE. But he always reads Fogler and Levenspiel only. He doesn't read, let's say, X institute material, Y institute material, Z institute materials. No. So he always goes to Levenspiel and Fogler before setting up the GATE questions only. No. That is a minimum common sense. That is why I always prefer to solve the textbook examples, back-end questions, and textbook concepts. Not, let's say, my preference least for the, let's say, the mock tests, or let's say practice tests. That is only for practice. Clear? So we will solve another question in the step input. In the step input. So this is the step input where you have injected, let's say, take 5 moles. Calculate what is T bar and what is V. This is concentration with respect to time. So today onwards, what we do is after completing the class, for the doubts clarification, you raise your hands. If you are sending in chats, I am well and good. If you could not able to send your doubt in chats, you just raise your hand. I will unmute you so that you can ask in voice also. See, 1 minute is the answer. Or so what is T bar? T bar means here, remember, you are writing the concentration integral because you are interested in this area. Zero to C max T DC. TDC 1 by C max. So what is 1 by C max? 1 divided by 2. 0 to 2. T into DC. Now when the concentration is changing from 0 to 2, how your time is changing 2 to 4 as per the straight line? What is the straight line equation? 2, 0. 2, 0. This is 4, 2. So how do you write this straight line equation? Is C minus 0 by T minus 2 equal to 2 minus 0 by 4 minus 2. Straight line equation. What is C is 2C plus 2 is T. 1 by 2 into 0 to 2. 2C plus 2 into DC. 2, 2, 2 here will cancel. C plus 1 DC. You don't need to find out area here. Remember here, you can't say T bar is something which divides area into equal parts because statistics wise, you are finding average of X, whereas mass is located on the Y side. Yeah, this is divided by 2. So what is T is basically C plus 1. C plus 2, no? Just write the straight line equation and substitute here. T is C plus 2. Half into 0 to 2. C plus 2 into DC. So what is T bar coming? 3 minutes. T bar. Once you get T bar, how do you calculate V? So what is C max is equal to m dot by V. This is what is, if your experiment is right. If you are doing this experiment in the lab, you have to check this one. But if it is given in the question, that means it is already checked. So this is 2. What is m dot given? 5, no? 5 divided by V. So what is V is 2.5. Then what is volume of the reactor is 2.5 into 3, which is 7.5. This is what is volume. See, this equation is step experiment equation. Clear? So what is Cmax given in the question is 2, no. What is m dot given in the question is also 5. So what is V is 5 divided by 2, which is 2.5. Cmax is this value. What is Cmax is, this is what is called as Cmax. In your notes, if you write, go back. What is m dot is, this much amount of red fluid is continuously added. If you see in the pulse experiments, for red fluid, there is no minute term because you are injecting only for one time. Here it is a continuous fluid. So V is 2.5 into 3, which is 7.5. Step experiments may not start from origin. Reason because when you start the red fluid, the reactor is filled with white fluid, no? So that white fluid has to go out, then only red will come out of the reactor. No? Yes, it is should be mentioned in the question that pulse or step experiment. Curve may not be straight line sometimes. If the gate questions, you will get a straight line equations. Generally in your labs, you will not get a straight line equation. So in your lab, how do you get this type of experiments is something like this. There, how do you do this area is by trapezoidal rule, Simpson's rule, or let's say, if you are plotting on a graph, you will count the boxes and then that procedure and all is there. So everybody done up to this point? We'll go to next important thing, which is how does RTDs look for a ideal reactors? No, it will be given in the question that 100% whether it is step input or pulse input. Next important point is RTD of ideal reactors. RTD of ideal reactors. Now just take 2 minutes time and read the pulse input and step input again. So then you have to draw what is the RTD for, let's say, CSTR, PFR, or let's say CSTR followed by PFR, 2 PFRs in series. So now this requires complete technical knowledge of CSTR and PFR. If you could able to draw an RTD of a combination of ideal reactors, I think you have understood 200% of the concept of ideal reactors. So imagine that even without the concept also you can solve the problem when you know PFR equation, when you know CSTR equation. But this RTDs you can draw only when you have a complete knowledge of a reactors. Let's take a CSTR of 100 meter cube volume. Let's say I am sending fluid of 10 meter cube. Let's, for time being, we will draw only pulse inputs because pulse inputs are easy to understand and important for gate point of view also. Let's say this is where I am injecting my pulse. This is where I am observing. This is where I am injecting. This is where I am measuring. Can you draw how RTD of an ideal reactor look? First, to draw the shape of the RTD. Can you draw what is the RTD of a PFR? This is what we are writing is a ideal PFR. What do you get as a vertical straight line? Is it right? Why do you get vertical straight line? So straight line then parallel to x-axis after some point. Somebody is saying straight line with a constant slope. Horizontal straight line starting at a little late. So I'm getting mixed answers. I got replies. Somebody says complete straight line. So each and every pass, somebody says concentration uniform in PFR. So vertical straight line. So somebody says straight line with slope. Somebody says vertical line followed by horizontal line. Once again, I got another straight line perpendicular to x-axis, vertical straight line, horizontal straight line. What is pulse input? You are putting all the red particles at same time, no? At time t equal to 0 on a single plane. On a single plane. Clear? Now, imagine that planes are going into the reactor and planes are coming out of the reactor. See, imagine this has to be completely, our brain has to be 100% working here. See, planes are, imagine that planes are going into the reactor, planes are coming out of the, let's imagine that PFR. So we'll understand differently, slightly differently. Let's say PFR is a reactor where every person is entering into the reactor and person is coming out of the reactor. Clear? Imagine that every person is a plane. Imagine that, let's imagine that every person is a plane. Suppose if you give 100 red particles to some person which is entering into the reactor, after entering inside the reactor, does he shares these red molecules with others or does he only holds the red molecules? He only holds it, no? Or he will share it with the rest of the people. Then when he comes out, where do you find all the 100 molecules? Only with him only, no? Clear? So that red molecules you will get on a same plane. So imagine that that plane is one person. So when that plane comes out of the reactor, you will get as a straight line. What is CSTR? Suppose let's imagine that that occupancy of the reactor is 10 people. At any point of time, that reactor has 10 people. So the person who has entered with 100 red particles, immediately he entered, he will share that 100 red particles with everybody. With everybody. So that is what is CSTR. Equal sharing of the molecules on each planes is called as CSTR. No sharing between the planes is called as PFR. Now at what time you will get this PFR? At what time you will get this peak? Equal say we back mixing, yes. Equal sharing is called as back mixing, 100%. At what time? So here I have given the numbers also. Suppose, imagine that you are injecting here, no? You take 2 minutes to travel to the reactor. It takes, let's say, 5 minutes to reach to measuring point. Now, it takes 2 minutes to reach reactor. How much time it spends inside the reactor? 10 minutes. And what is out time? 5 minutes. Where do you get peak actually? After 17 minutes. But I don't consider these values while writing RTD. Because I will consider only 10 minutes. Why I have not taken this 2 minutes and 5 minutes while writing the peak? Because what is this T? This T indicates age of particles. Age of particles, or let's say residence time of particles. Suppose if I write 17 minutes there, you will misunderstood that every particle has experienced 17 minutes of time inside the reactor, which is not true, no. Particles has experienced only 10 minutes inside the reactor because this is the time where your, let's say, reaction is happening. So whether part in this 2 minutes, in this 5 minutes time, in this 2 minutes, in this 5 minutes time, even the particles are spending time inside the pipe. They are not reacting because there is no temperature and pressure, no. So this time should be only age of particles. So or let's say residence time of particles. Clear? So that is why. So spend some time. I'm going to give, let's say, 2 minutes or 3 minutes after each ideal reactor RTD. So you have to understood completely, and whatever you understood from the class, write on your notes, because this is something which is slightly confusing topic in the chapter 4. How do you draw RTD of ideal reactors? Because you will understand now, but when you open the notes after a month, I want everybody to get, let's say, I will explain one more time, don't worry. 10 because it has spent time 10 minutes. No, what is residence time here? 100 meter cube divided by 10 meter cube per minute, which is, what is residence time is 10 minutes. No, because we are not saying this 2 minutes or 5 minutes are not residence time, because they are not inside the reactor. No, they are not inside the reactors. They are outside the reactor. Outside the reactor, whatever the time spent doesn't matter to me, because that is not useful for the reaction. So space time is different. I'll explain in the, let's say, later on classes what is difference between, let's say, residence time and space time, but don't get confused here. That will come in gas phase reactions. Concentration will vary in PFR, but if you inject the red molecules, that red molecules will come out as a single plane. So just spend 1 minute time. I'll explain one more time. So I'll explain one more time. So in PFR, suppose You are sending the planes and planes are coming in. Planes are going into the reactor, planes are coming out of the reactor. Suddenly you injected a plane of red molecules. So that plane of red molecules will travel like this. So will travel like this, will travel like this, this plane of red molecules. So finally that plane of red molecules will come as it is as a plane of molecules. That red molecules will not be shared by anybody inside the reactor. So that is how the, what is this RTD is nothing but how that red molecules, if you inject 100 red molecules, how that red molecules are coming out of the reactor. So are you with me? 100 red molecules exit at the same time because you injected 100 red molecules at the same time, no? So this is what is E curve with respect to time. This is an ideal PFR. Same residence time means a vertical line, not horizontal line. Suppose if I have horizontal line, if I draw a horizontal line like this, what does that mean? Some particles has this residence time, some particles has this residence time, some particles has this residence time. What is x-axis? Residence time, no. Residence time same means all the particles will have a same RTD. So we'll move to, everybody understood here, we'll move to CSTR. So step input we will talk, only pulse inputs we are different talking here. 8 point of view, pulse inputs are important. So before going into step input, let's say CSTR, let's imagine that. So CSTR defined like this. Let's say inside you have 4 people. So continuously there is one person per minute goes and one person per minute enters. This is a steady state. This is how the reactor only, no? There is some molecules entering, some molecules are inside, some molecules are going. Clear? So everybody could able to see the doubts. So I think I missed to change the settings to host only. So have you understood this one? How a reactor is? What happens is when a new person enters here, one person will exit from here, but all the 4 persons will share everything is what is CSTR. Suppose suddenly at time t equal to 0, you give 100 red particles. So to this person who is entering, person is a plane. So you are giving 100 particles. Now this, when this person enters, who is carrying the person enters the reactor, there will be one person who is exiting the reactor. That person will not have any red molecules, no? Now, when this person who is carrying the 100 red particles enters the reactor, all the 4 people will share these red particles, or only that person will keep that 100 particles? Share. So sharing means equal sharing, no? So this, so what is the first plane? So this 100 particles will be shared by all the molecule, all the 4 people. So each person will get 25 molecules. So at time t equal to 0, at time t equal to 0, this is like this. Everybody this person will have 25, this person will have 25, this person will have 25, this person will have 25 at time t equal to 0. The person who is exiting, that means a person is ready to enter, no? That person who is entering doesn't have any red molecules, because pulse input means you are injecting only once. So the person who is exiting will take the 25 molecules. So the first plane at time t equal to 0 comes, will have a 25 particles. So you will get one doubt here. Addition of pulse, sharing of the molecules coming out of the reactors, there will be some delay, no? So can I put 25 particles here? Is the doubt that you will get. But what is ideal CSTR means? Addition of pulse will take 0 minutes. Mixing also will take 0 minutes. So the first person who comes out will carry out is also 2 minutes, 0 minutes. So on y-axis, first you will observe 25 particles coming out of the reactor. Did you get up to this point? If I put 100 particles inside the CSTR, how that 100 particles will come out of the reactor? So imagine that there are 4 people inside the room. So you have given 100 red balloons to them. So everybody will share equal. So every person will get 25 red particles, no? Red balloons. So the person who comes out first will have how many red balloons? 25 red balloons. No, that is what I have written. Why it is time t equal to 0? Because the addition of pulse, mixing and coming out, it is an ideal system. What is an ideal system is, addition of pulse will be 0 minutes, mixing will be 0 minutes, and coming out is also at 0 minutes. So all these things will happen instantly. That means 0 minutes. That is what is ideal. But reality is different. Now, when a person who is carrying, let's say, 25 red molecules come out here. So let's say I will write at t equal to 0.1 minutes. Then what is the reactor status? When this 25 goes out, how many red particles will have? 75, no? The person who is entering doesn't have any red particles, no? So at any time you have 4 people inside the house. What will be the each person red particles? 75 by 4. 75 by 4, 75 by 4, 75 by 4. So the person who is exiting next will carry how many red particles? So the second person who is exiting after some time will carry 75 by 4 red particles. (75) will be shared by all people, which is 18.75 molecules. Now what is left? 17.5 out of this one, 80.75 is left. So what is left by the is shared by all the people. So that is how. So you will get an RTD, which is, this is how the RTD. So what is RTD of a CSTR is something like this. Now I will leave you for, let's say, 3 minutes or 4 minutes. Just understand again. It will go to 0 at infinity time. What is difference between time coming? That will be depends upon, let's say, flow rates and all, but after some time. So whatever we are drawing is, let's say, concentration versus time. Now I'm going to derive what is the equation for this curve. But first thing is you have to understand how this curve is coming. So E curve, C curve doesn't matter for PFR because it is straight line only. No? There is no derivation for PFR because it is straight line, then there is no derivation. No? But here there will be a derivation. So you injected 100 red particles, or 100 red particles will be shared by all the people. So everybody will get 25. So the person who carries first will be 25. Now you have 75. 75 will be shared by 4. So next person will be 18.75. So next will be, let's say, 75 minus 18. So that will be shared by all the 4 people. Let's take 75. Let's take this as 19. So what is 75 minus 19 is 56. 56 will be shared by 4 people. That is what is next point. So that person entering, person exiting will be continuously happening, no? Your reactor cannot be, this is a continuous reactor, no? Here, if everybody is clear, then I'll move to, let's say, derivation of this CSTR. Now let's take V volume of CSTR. There is a flow rate of V and V going into the reactor. Let's say white fluid is going into the reactor, white fluid is coming out of the reactor. Now at time t equal to 0, m moles of red fluid is added into the reactor. This is what is pulse input, no? Then what is concentration of red fluid at the rate of time t equal to 0? If injected m moles of red fluid into the CSTR of volume V, then what is the concentration of red fluid at time t equal to 0? M divided by V, no? If added m moles of red fluid into V volume, then what is the concentration? So the first plane the first plane which comes out will have a how much concentration? C naught, which is nothing but m divided by v. See, the first plane which comes out will have a, and then concentration of red fluid will be slowly decreases because of the previous logics that we have written. Now we will write a balance on red fluid after adding. After you add, we will write a balance on red fluid. So that is red into the reactor is equal to red out plus red accumulation. Is it steady state or unsteady state? Unsteady state. This is white fluid, it is steady state. Red fluid, it is unsteady state. Because red I injected 100, slowly that 100 is coming out now. Initially 25 came, later on 18 came, later on 15 came, later on 12 came. So that red fluid will be slowly depleting out of the reactor. So with respect to red fluid, it is unsteady state. So I'm writing balance on the red fluid after adding. I'm writing balance on the red fluid after you've injected the 100 molecules. What is red into the reactor? Are you continuously adding the red fluid? So what is red into the reactor is 0. So here you will get a confusion. I have added m moles of red fluid, but why you are writing this red into the reactor as 0? That is why I have written, I am writing balance on the red fluid after addition. Suppose if I add, once I add the red fluid into the reactor, how that red is coming out of the reactor is this balance. This balance is how that red is coming out of the reactor. So what is in is 0. What is out? Outlet volumetric flow rate is V and outlet concentration is C. What is accumulation? D into Vc divided by dt. What is C? What is C is concentration. What is C is what is C is concentration of red fluid at time t. So this, understand this equation. What is V into C? How many moles of red fluid? What is V into C? After adding m moles of red fluid, how that m is coming out of the reactor is what is this balance. At any time, this is how the balance is. Red in is equal to 0, red out is V into C, red accumulation is V into C. Just take 2 minutes time and understand this equation and continuously derive this equation from now onwards. Why it is 0? Because I added, after I am writing this balance after addition of red fluid. So I added 100 molecules of red fluid into the reactor. That is only one time activity. Now, how that 100 coming out of the reactor is what I am writing the balance. Just complete this derivation. I kept on mute for some time so that you will understand. I am not speaking anything. So now if you derive this equation further, this V is, you can take out of the integral 0 equal to V C V into dc by dt. This C is what? Concentration inside the reactor. This C is concentration inside the reactor. This C is concentration exit of the reactor, but both will be same. So that because it is a CSTR. So if I take this V here, this will become dc by dt is equal to C by tau, which is equal to 0. So what is dCb by dt equal to minus C by tau. So what is dCb by C equal to minus dt by tau, integrated from C naught to C, 0 to T. So this will become ln C by C naught is equal to minus T by tau. What is C is C naught into e power minus T by tau. This is what is C equal to C naught. So I am just showing the previous board also. dCb by dt equal to C by tau. dCb by dt plus C by tau is equal to 0. Slowly that red fluid is depleting. So I'm taking to next board. Now what is RTD that you have drawn is, this is, the graph is C naught, the equation is C naught into e power minus T by tau. This is concentration versus time. Can somebody draw the E curve for this one? When concentration becomes 0, when T tends to infinity, that means that slowly, that means if you visualize immediately, when you add red fluid, immediately dark red, slowly that darkness will become decreases, and finally when it becomes 0 is, it will be infinity time. Tau is what is residence time, no? Residence time of CSTR. C naught is not slope. C naught is the initial point. Now, what is area of this curve? What is area of this curve is integral 0 to infinity c dt. So, integral 0 to infinity c naught into e power minus t by tau into dt. So, what do you get this as? C naught into tau, area. If you solve that integral, you will get C naught into tau. Then what is E coordinate? What is E coordinate is nothing but where do you get everybody C naught into tau? C by area. What is C is C naught into e power minus t by tau by C naught into tau. What is E curve is 1 by tau into e power minus t by tau. So what is E curve is 1 by tau into e power minus t by tau. What is the starting point is? This is E versus time. For a CSTR. So I'm showing the previous slide. So this integral is, if you solve this integral, you will get, what is this integral? Maybe I'll derive. C naught divided by 1 by tau minus into e power minus t by tau with the limits of 0 and infinity. That is where you will get C naught into tau. T is at that time, tau is the, then what is E by? E equal to C by A, C naught into e power minus t by tau, C naught into tau equal to 1 by tau into e power minus t by tau. So if you plot this one, E time 1 by tau into e power minus t by tau. This is how. What is the starting point? When you put t equal to 0, the starting point is 1 by tau. 1 by tau, this curve starts at 1 by tau. Now just take 1 minute time and read the entire CSTR RTD again. So clear? Now what is the next RTD is, suppose if I have PFR followed by a CSTR. In series, let's say you are injecting here and you are observing here. Volume of the PFR is Vp, volume of the CSTR is Vm. So volumetric flow rate is VR. So how do you, now both combinedly you have to write. RTD means here you have to combine both and then write. How does the RTD looks like? So somebody asking to show the previous slides, I am showing it once. So you have a CSPFR followed by CSTR. So you are observing here, you are injecting here, volumetric flow rate V, Vp and Vm. Pulse input only. I told all the things that we are doing are pulse inputs only. Just you have to visualize, if I put a plane of red molecules, how does it will go to PFR? After PFR, what happens? Now, after that after PFR thing goes to CSTR, what happens? So I got multiple answers. So somebody's answer is it will resemble the graph of CSTR, only that the graph will not start from time t equal to 0. Correct. But at what time it will start? Where? So it will be like an impulse response. So I'm not getting. RTD shifts by P divided tau residence time, right? Vertical and then exponential, right? Line parallel to time, then decreasing. Not correct. I think identical to CST or RTD. Identical, but does it starts from time t equal to 0 is my question. Yes, we get the same result as ideal CSTR, but after the residence time of PFR. Correct. So I think I am got most of the exponential shift by tau p time. Correct. I got at least 10-15 replies. Correct replies. So imagine that, let's say you have injected a plane of molecules here. What happens when that plane will come here? After tau p minutes, that plane will come here. So without PFR, what happens is you are injecting that plane at time t equal to 0. With the PFR, what happens is the time is delayed by pulse, because PFR doesn't do anything to the RTD. Whatever comes in will go out of the reactor is PFR. So you have given a straight line, you have given a plane of molecules, that plane will come out as it is. So what happens here is the plane of molecules will be shifted by this much. The first thing that you will observe is after tau p minutes. That means imagine that this combination is nothing but a CSTR. You are giving the input delayed by tau p minutes. Correct. You are giving the input delayed by tau p minutes. Then what happens to the equation? 1 by tau m e power minus t by tau m is your RTD of CSTR, no? But your input is delayed by tau p minutes. What is t minus tau p is the equation. Your time is just replaced by t minus tau p. Somebody has asked already, what happens if you put CSTR first and followed by PFR? Very good. That is my next combination. CSTR first followed by PFR. That is my next. So if you guess, the pen is not coming, let's say, thick enough. So I'll try again. So you are injecting here. So this as a whole you need to draw the RTD. What is RTD here? Somebody started same as previous one, sir. Same as single CSTR RTD. Not correct. Here also PFR won't have any, so it will be similar to CSTR. Okay. Plot is similar to above, declining curve. So I got 2-3 correct replies. So just imagine that if you put 100 particles into CSTR, how they will come out of the CSTR. Now the coming out particles will go to PFR, then what happens? Just think for 2-3 minutes and then solve. So what happens here is, suppose if I put, let's say, at time t equal to 0, this is how it will come out, no? What is starting point? 1 by tau. Now this curve goes to PFR, what happens? Does this curve shape changes? Only thing is the entire curve will be shifted by tau p minutes. Nothing will happen. So exactly same, no? Both are equal. Doesn't matter. But you will ask, PFR followed by CSTR is good for second order, no? Greater than 1. Here I got our same RTDs because these are non-reactive fluids. T in your previous expressions is time, no. It is simple time because you are plotting this graph with respect to time. Equation will also be same, no. Here basically input is delayed, here output is delayed. But you are observing here, no, it doesn't matter whether input delayed, output delayed, you don't see anything. I think we'll stop here. I have some more RTDs, let's say 2 PFRs in parallel, 2 PFRs in series, PFR CSTR in series, let's say recycle CSTR, recycle PFR. So that some more RTCs that we will discuss tomorrow. I have 10 minutes for the doubts. So today what we will do is, you can ask doubts in the chat session, or you raise your hand. I will unmute you. You can ask verbally. So last graph somebody is asking to explain, because see, I put, let's say, time t equal to 0. This is my RTD. Then this is how the RTD is splitted by CSTR. Now this entire graph goes to the PFR. It doesn't change anything, no. PFR, whatever comes in goes out of the PFR as it is, only time is delayed by tau p minutes. So please share your doubts. No, they doesn't interchange, no, because it is just a delay. See, if I don't have PFR here, your time is T. If I have PFR here, whether it is first or second, doesn't matter, no, because see, for you, this is a closed open loop. This is a closed system. Here input is delayed, here output is delayed. Basically, when you are standing here, it doesn't matter. You are observing here, no? So your time is delayed by tau p minutes. Sir, this time GATE we can give 2 papers for chemical engineering. Everyone will give other 3 options of chemistry, petroleum and engineering sciences. Engineering sciences will have most syllabus, no? Chemistry, chemical paper. Chemistry will not do. Petroleum, this is every year, not only this year. Chemistry people can write chemical engineering GATE. Petroleum also people can write chemical engineering GATE. I think chemistry is added this year. Engineering sciences will have more, I think. So what is the meaning? What do you meaning residence time? What is mean residence time? Residence time is tau, no? Can the last RTD of PFR be treated as multiple? Because see, multiple spikes is nothing but this continuous line. No, continuous line is nothing but because of multiple spikes. Because it is continuously coming. Yes, yes, multiple spikes with the heads are connected. That is what I did, which is a decreasing curve. Because every plane carries some molecules, no? So how did you get this equation is, as a CSTR is E1 by tau m into e power minus t by tau m. Because your times are delayed by tau p minutes, no, that is t minus tau p. That is why time delay is captured in t minus tau p. So anybody wants to ask orally doubts? I can unmute you, you can ask. See, if I am not getting any doubts, meaning that I'll consider that everybody understood the topics. Here y-axis represents E. So I'm not sure what subjects comes. I think you have the syllabus now. Maybe better to check with the syllabus. You have the chemistry syllabus, petroleum syllabus, engineering science. But it doesn't matter to you, no. Because if you are studying chemical engineering, write chemical engineering gate. Put it as chemical engineering. If you are studying petroleum, generally, I think last time what happens is petroleum people can also write chemical engineering gate. Right now, I think they are shifting slightly differently for the petroleum people, because petroleum people 2 semesters they will study about the upstream petroleum exploration and downstream refinery. That is where I think they want to put more syllabus onto petroleum. So somebody is asking to explain the graph again. So at time t equal to 0, this is the one. After residence time, this is how it splits. Then this goes to PFR. That is how it comes out. So I recommend you to listen to this video again, so that actually if you have any doubts, you will. So any doubts more? Does anybody want to ask, let's say? So I got read out in the derivation how it is VC. VC because what is V into C is what is V volume of the fluid V. What is C is concentration. Basically you have to write dN by dt, which is what is accumulation. Accumulation is dN, moles accumulation with respect to time. How do you write moles? Volume into concentration, no? So how do you write is, what is accumulation? What is accumulation time is dN by dt. What is N moles of red fluid? How do you get moles? Volume multiplied by concentration. Red out is small vc, because outlet volumetric flow rate is V, outlet concentration is C. So V into C. This is what is moles per minute. This is moles per minute which is going in. What is molar flow rate is nothing but volumetric flow rate into concentration. No? Any doubts? V into C. C concentration. Does reduced volume has practical use? I am not getting reduced volume. What is meant by reduced volume? How can delay before or after have the same looking graphs? Because it doesn't matter, no. What you are observing here, no, you are standing here. You are standing here. So assuming that this is completely closed. This is completely closed. It doesn't mean that whether input is delayed or output is delayed. You are standing here. Suppose if you are standing in between, then it matters to you. Got it? What is V by Vc? No, this is not V suffix C. V into C. Is RTD done for gas phase? RTD is simple, doesn't matter whether it is gas phase or liquid phase reactions. RTD is for particle enters inside the reactors. We are talking about planes. Planes are same, no? Whether it is liquid or gas. Any doubts? Yeah, I will share MSUB PDF copy. So okay, I'm closing the session.